Good morning everybody, and welcome back to another video on electronics. In the last video, I said that if this was a perfect conductor, and if this was a perfect conductor, then the current of the whole circuit would be determined by this one resistor. And we're able to use Ohm's law to work out what that current would be. So if you had a 100 ohm resistor here, and you have a 1.5 battery here, then the current is going to equal the voltage divided by our resistance, which means it's going to equal 1.5 divided by 100, or 0.015. But now, I want to do something kind of tricky. Now I want to have two 100 ohm resistors. And just so we have round numbers, I might change this from 1.5 volts to 4 volts. So, what do you think the current of this circuit is going to be? Firstly, if we still use Kirchhoff's current law, we still know that any amount of current coming out of here has to be the same as the current coming out of here, has to be the same as the current coming here, has to be the same there, has to be the same here, has to be the same here. Current going in has to equal the current going out, and because we have a straight line, the current must be the same along the straight line. So what is that one current? Well, if you isolated one part of the circuit and tried to use the same formula as before, where I is equal to V over R, then you're going to have an answer of 0.04 milliamps. But that isn't quite correct, because even though this resistor has the same value, that does not mean that the current going from here to here is experiencing the same amount of resistance as though there was only one of them. It faces a certain amount of resistance here, and then it faces even more resistance here. So it actually faces double the resistance it would if there was only one of these 100 ohm resistors. So because it faces resistance here and resistance here, what we do is we add up the resistances that it faces into a large total resistance. So 100 plus 100, that is equal to 200 ohms of resistance. So the current is going to equal 4 volts divided by 200 ohms, which is going to equal 0.02 amps, or 20 milliamps. When we have one resistor connected to another resistor in a straight line like this, we say that they are connected in series. And it kind of makes sense why you'd add them up. If you think of them as just being material that current has to travel through, you're making the road twice as long for the current. So even if it is facing the same resistance, which sometimes they're not, sometimes this can be much higher than this one, but say if they were facing the same resistance, they're facing the same resistance over double the length. They're facing the same resistance twice. Now, similar to last time, we have two resistors, but instead of being connected end to end, both ends are connected to one side and both ends are connected to another side. And so this is what we call resistors being in parallel. Kirchhoff's current law no longer really applies here because we have a branch. It's no longer a straight line. And if these resistances were different, say if we have 100 there and 200 there, then there might be half the current going here as there is through here. But the good thing about Kirchhoff's current law is that it doesn't just apply to a single component. If we draw a box around these parallel resistors here, then the current going into that box has to be equal to the current going out of that box. So if you wanted to find the current of the circuit, there is still a current of the circuit outside these two resistors. And there is a trick where you can combine these two resistors to sort of make one hypothetical resistor with one value. And I want to teach you something that helps my intuition to figure out things like this. There's this value in science and electronics called conductance. And we don't use this value very much. We mostly work with resistance. But conductance is sort of the opposite of resistance. If you have a highly conductive metal, it has very low resistance but very high conductance. And then if you have a sheet of plastic that's an insulator, it has very low conductance but extremely high resistance. So basically, conductance is the inverse of resistance. And likewise, resistance is the inverse of conductance. If we have a path that the current can travel through, going from point A to point B, maybe it's like a low resistor, is going to have some sort of high level of conductance. Now, if we copy this path and we have two of exactly the same paths, what do you think is going to happen to the conductance? Well, if you've got two of exactly the same paths, then you can send twice the amount of charge from point A to point B at once. So assuming these are the same, then the conductance is going to be double whatever the conductance of the first one is. But what if these conductances were different? What if you had high conductance on the top one and you had low conductance on the bottom one? Well, you can call one C1 and you can call one C2. And you might say, instead of being double, the total conductance, so CT, is going to equal the conductance of the first path plus the conductance of the second path. Even if you can send less charge, it's still additional charge. And I hope that this really makes sense to you, because this next part probably doesn't make sense unless you try and think of it like this. But let's try and replace this conductance with resistance, which is more helpful for us in circuits. So we have an R1 and we have an R2. Now remember, resistance is just the inverse of conductance, right? It's the opposite. Something highly conductive is not very resistant. 1 over RT, or the total resistance, 1 over the total resistance, is going to equal one over R1. That's all C1 is, right? C1 is just 1 over R1, and C2 is just 1 over R2. 1 over total resistance is equal to 1 over R1 plus 1 over R2, which doesn't make for a very nice formula, but I hope now you can understand sort of how we got there. So coming back to this problem, if we imagine we want to find the total resistance across here by pretending this is a box with just an input and an output, and we want to combine the resistance of these two resistors right here, then we can use this formula. So we can say 1 over R total is equal to 1 over 200 ohms plus 1 over 100 ohms. Now, you can't just add the 100 and the 200 together because they're fractions. It doesn't work like that. You can't add a third and a half and get a fifth. So we have to make a common denominator. So we can say 1 over RT is equal to 1 over 200 plus 2 over 200. Right? We just multiply the top and the bottom. And I can already see that I haven't really done myself a favor with these numbers. 1 over RT is equal to 3 over 200, which means RT is equal to 200 divided by 3, or it's also equal to 66 ohms. 66 ohms? Is that correct? But we have two resistors that aren't small. One of them's 200 ohms, and somehow the total thing combined is only 66 ohms? Yes. It's always going to be less. Think about it. There are now two paths that the current can go through. We're actually adding conductance because we've got two conductive paths here. There's going to be a lot less resistance than if there's only one path.